Hello students, today we are going to see a very important topic, valence bond theory in chemical bonding chapter of class 11. This theory arises due to the limitations of valence shell electron pair repulsion theory. No doubt, valence shell electron pair repulsion theory is able to explain the shape of simple molecules, but it is unable to predict the shape in a number of cases. Also, the direction of electron pairs does not seem to be convincing because the geometries of the molecules is based on the repulsion of bond pair and lone pair of electrons on the valence shell of the central atom. In order to address these issues, the two theories have been put forward. The one is the valence bond theory, the other one is molecular orbital theory. In this video, we shall discuss about the valence bond theory. This valence bond theory considers the two concepts. One is energy concept, the another one is orbital overlap concept. Let us see the formation of hydrogen molecule using this energy concept. We know the hydrogen atom has one electron, its electronic configuration is 1s1, that is 1s orbital is spherical in shape. So hydrogen atom has one electron, another hydrogen atom has one electron. They approach each other and forms the hydrogen molecule, H bond H. This is a covalent bond. Right? Let us see how this hydrogen molecule is formed using this energy concept. Suppose we have two hydrogen atoms, HA and HB, kept at infinite distance from each other. Then there will be no interaction between them, but there will be interaction between nucleus of hydrogen atom A, Na, and the electron of the same hydrogen atom A, that is Na and Ea. Na is the nucleus of hydrogen atom A, Ea is the electron of the hydrogen atom A. There will be a force of attraction between this nucleus and the electron. Similarly, this is HB. There will be interaction between force of attraction between the nucleus of hydrogen atom B and its own electron Eb. But there won't be any interaction between them when they between the two isolated atoms when they are infinite distant from one another. Now, what happens when they begin come to closer? As they begin to come closer, the new forces of attraction as well as the forces of repulsion also operates. So this is the situation when the two atoms close each other. There will be new forces of attraction as well as repulsion happens. What is the new forces of attraction? When they approach each other, this nucleus of hydrogen atom A attracts electron of hydrogen atom B. So therefore, the interaction between them, this is a force of attraction, new force of attraction. And here also, there will be a force of attraction operates between nucleus of hydrogen atom B and the electron of hydrogen atom A. So these green lines are the new forces of attraction, and this is the old force of attraction that was already present between the nucleus of hydrogen atom A and its own electron, and the nucleus of hydrogen atom B and its own electron. So there will be four attractive forces here, two old force of attraction and two new force of attraction. When they approach each other, not only the force of attraction, the force of repulsion also operates. The repulsion forces operate between the two like charges. Here the electron of A repels with the electron of B, hydrogen atom B. So the repulsive force operates between electron of hydrogen atom A and hydrogen atom B. This is the repulsive force. Also, the repulsive forces between nucleus of hydrogen atom A and the nucleus of the hydrogen atom B. So there are only two forces of repulsion. There are four attractive forces and two repulsive forces. Okay. Let us consider the formation of hydrogen molecule graphically. The energy changes can be represented in the graphical form. We have a graphical representation here between potential energy and internuclear distances. As the atoms stay far apart from each other, okay, the energy of the system is almost zero. As there are many the large internuclear distance, the energy is almost zero. But as they come closer to each other, okay, as they come close to each other, the system start losing its energy. The system start losing its energy because the force of attraction exceeds the force of repulsion. So system start losing its energy, the graph goes down. Okay, but at a certain equilibrium distance, the forces of attraction and repulsions are just balanced. The force of attractions and repulsions are balanced. And in this case, the energy of the system becomes very, very minimum, which means the system is attained a stable state that is called a molecular state. At this state, the bond is formed. At this particular internuclear distance, we say that bond is formed. Right. So when the bond is formed, at this particular internuclear distance, this hydrogen-hydrogen bond is formed. The bond length is the distance between the two internuclear distance is the bond length here. That is your 74 picometers. Also, when the atoms approach closer, the energy keep on decreasing, and it reaches a minimum state for a stable state is formed. Okay, this much of energy is released when the stable state is formed. How much of energy is released is correspond to this 435.8, actually is negative, minus 435.8 kilojoules per mole of energy is released when the hydrogen bond, covalent bond formed between hydrogen atom and the hydrogen atom. Which means that in order to break this covalent bond, we need to supply the 435.5 kilojoules, 435.8 kilojoules per mole. In order to break this bond, we have to supply this much of energy. Therefore, this energy is called bond enthalpy. So at this stage, the molecule is formed. That is, the system has attained a very, very minimum energy state. Minimum energy means maximum stability. Therefore, the molecule is formed. The stable molecule is formed at this state. Okay. What happens if we try to bring these atoms, these two hydrogen atoms, still closer? What happens? Then the repulsive forces start operating, start overpowering the attractive forces. The repulsive forces dominate the attractive forces. If the repulsive forces is more, the system again, the energy of the system increases, therefore it becomes unstable. So if you try to bring atoms closer, the repulsive forces start overcounting the attractive forces. Therefore, the energy of the system rises, the molecule becomes unstable. That is, the molecule is not formed again in this stage. Okay. So this is the energy concept. Now let us see the formation of simple molecules or formation of covalent bonds between atoms in the molecules by using orbital overlap concept. According to this concept, when atomic orbitals of the approaching atoms, partially overlap, partially interpenetrate or overlap, the lowering of energy takes place. Therefore, the stable bond is formed. That is, a covalent bond is formed by the partial overlap of two half-filled atomic orbitals containing electrons with opposite spin. That is very, very important point in this aspect here. The covalent bond is formed by the partial overlap of two half-filled atomic orbitals. If an atomic orbital has fulfilled, that is, if it has two electrons, the overlap will not take place. Overlap does not occur. They should have half-filled orbitals. The electron should be, half-filled. The orbital should be half-filled. Then only the overlap takes place. Okay. So the partial overlap means that a part of electron cloud of each of the two half-filled atomic orbitals become common. As a result, the probability of finding electrons in the region of overlap is much more than in other places. Also, the strength of the bond depends on the extent of overlap. Greater the overlapping, stronger is the bond formed. To see the formation of hydrogen molecule here. So in this example I discussed hydrogen molecule. what happens when two hydrogen atoms having electrons with opposite spin come close to each other, the s orbitals overlap with each other, resulting in the formation of a molecule. H2 is a molecule. Stable covalent bond is formed. One more example we discuss, the hydrogen fluoride molecule, HF molecule here. The hydrogen atom has one electron, its electronic configuration 1s1, and fluorine is having 9 electrons, 1s2, 2s2, 2px2, 2py2, and 2pz1. Okay. According to the orbital overlap concept, as I told, the orbitals should have half-filled configuration. That is, orbital should have one unpaired electron. It should be singly filled. If there are 2 electrons, they won't be involved in the overlap of atomic orbital. These orbitals will not involve in the overlapping. The orbitals having one unpaired electron will involve in the overlap. The hydrogen atom having 1s1 electron, 1s1 configuration is 1s atomic orbital of hydrogen with 1 electron with the clockwise spin. And these are the 3 2p orbitals of fluorine. 2pz is in this axis is internuclear axis, and 2px 2 electron, 2py 2 electron. As I told you earlier, these 2 orbitals will not involve with the overlapping. Only this orbital involved in the formation of bond. So this hydrogen and this 2pz having opposite spins, they overlap to form a bond like this. So here HF bond is, HF molecule is formed. Okay, now we'll see what are the types of covalent bonds. The covalent bonds are mainly of 2 types, sigma bond and pi bond, depending on the type of overlap. What is a sigma bond? When a bond is formed between 2 atoms by the overlap of their atomic orbitals along the internuclear axis, that is very important here. The bond is formed between 2 atoms by the overlap of atomic orbitals along the internuclear axis. This is said to be internuclear axis. Here this is the internuclear axis. This is internuclear axis. Then the bond formed is called sigma bond. Right. The overlap along the internuclear axis is also called end-to-end overlap or head-on overlap. The overlapping along internuclear axis can take place in any of these ways, these 3 ways. The SS overlap, which takes place along the internuclear axis, SP overlap takes place along internuclear axis, and PP overlap. And SS overlap, s orbital overlap, as we discussed in the hydrogen molecule here, like this. Right, the same example I given here. Hydrogen atom, one is 1 electron, another hydrogen atom, one is 1 electron with the opposite spin. The hydrogen molecule is formed with the bond H covalent bond. And SP overlap also takes place along the internuclear axis. S orbital is spherical, it is symmetrical, therefore it can combine with any p orbital. Right? HF, hydrogen 1s1 atomic orbital, 1s atomic orbital contain 1 electron. This is fluorine atom, as we discussed here. I omitted this 2px and 2py because they won't involve in the bond, overlapping, as they contain 2 electrons. So this orbital with 1 electron with opposite spin, they combine to form HF. A bond is formed between hydrogen and fluorine. And PP overlap also take place along the internuclear axis. 2pz and 2pz atomic orbital having 1 unpaired electron each with opposite spin, therefore the bond is formed. All these bonds are sigma bond. This sigma taking place along the internuclear axis, therefore this is also a sigma bond. This internuclear axis, the overlap take place along the internuclear axis forms a sigma bond. The electron density is more along the internuclear axis, therefore this must be a strong bond. Now we'll see what is pi bond. The pi bond is formed by the lateral or sidewise overlapping of p orbitals. That is, overlapping of p orbitals not along the internuclear axis. The sidewise overlap. See, this is internuclear axis, but this p orbital is right angle to this internuclear axis. Is not on the internuclear, is right angle to the internuclear axis. So there won't be any effective overlap here. They overlap sidewise. The interpenetration, the partial interpenetration or overlap is very little extent. So as a result, you have the electron cloud not along the internuclear axis but above and below the internuclear axis. Whereas on the sigma bond, the electron cloud is concentrated on the internuclear axis. Therefore, it's a strong bond. Let us see the formation of oxygen molecule. Oxygen molecule has two bonds, sigma bond and pi bond. In the case of oxygen molecule, the electronic configuration of oxygen atom is 1s2, 2s2, 2px2, 2py1 and 2pz1. This orbital will not involve in the overlapping because it is having two electrons in the same orbital. Okay, so we neglect this. So 2py1, 2pz1. This is 2pz is the internuclear axis. This is also 2pz internuclear axis. Addition is 2px, 2py, 2py. Okay, now what happens? These two orbitals on the internuclear axis, so therefore they combine along the internuclear axis to form a stable sigma bond. Whereas the electrons on the 2py orbitals with the opposite spin, they should combine sidewise, lateral overlapping take place, and they form a pi bond. Okay, here we need to talk about the strength of sigma and pi bond also. The strength of the sigma bond depends on the extent of overlapping. Since in the formation of sigma bond, overlapping is along the internuclear axis, therefore it is considered to be strong overlapping. Hence, sigma bond is the strongest bond. On the other hand, in the case of pi bond formation, the sidewise overlapping takes place, lateral overlapping, which is a very small extent, not along the internuclear axis also, therefore it's a weak bond. Thank you.